welcome Professor R. Balkrishnan to deliver his talk.
Professor R. Balakrishnan is currently an adjunct professor at Bharathidasan University, Tiruchirappalli. He has done his PhD from University of Maryland, USA, and MSc by research from Annamalai University. His main areas of research are algebraic graph theory and graph coloring. He has completed many funded research projects titled Energies of Graphs, Digraphs, and Sign Diagram, Factorizations and Decompositions of Graphs, etc. He published more than 50 publications at national and international levels. He has been a part of many international conferences and traveled widely to deliver invited talks in more than 35 universities. Currently, he is involved in organizing an outreach program in mathematics at Ramanujan University, Mathematical Society Building, National College campus at Tiruchirappalli for benefit of MSc, MPhil, and PhD scholars in mathematics. Sir, I request you to unmute yourself and deliver your talk.
Okay, it's Preetam. So, good afternoon, everyone. I am really sorry that there had been some problem in just showing up the correct slides. Let me take this opportunity to thank the departments of Mathematics of Amity University for the kind invitation that they have extended. Well, the title of my talk is the histochromatic number of a graph. All of you are familiar with graph coloring. So the main point is you color the vertices or edges. Suppose you want to color the vertices of the graph. If the graph has got n vertices, then we can assign one color to each. Then you get the n colors, and it so happens that adjacent vertices receive distinct colors. But that is uninteresting. What is interesting is you want to have the minimum number of colors required to color the vertices of the graph so that adjacent vertices receive distinct colors. Well, that minimum number is the chromatic number of the graph. One of the concept of coloring is a major area of research in graph theory, and they have got several coloring parameters, namely the chromatic number, the listochromatic number, or the choice number, and then you have the achromatic number, and so on and so forth.
So this is the first slide.
Finite and simple unless stated otherwise. And so what is the chromatic number of a graph? The chromatic number is the least number of colors required to color the vertices of the graph so that adjacent vertices receive distinct colors. You say that such a coloring is a proper coloring. Adjacent vertices getting distinct colors. Of course, if you give distinct colors to all the vertices, there are n vertices and you give n different colors, that is also a proper coloring, but that is uninteresting. What is interesting is the least number of colors that you require to color the vertices of the graph, which is the chromatic number. So next one, please. The listochromatic number is another coloring parameter of graph. So what is the listochromatic number? Or okay, you give a list, attach a list at each vertex. All of course are the same cardinality. You call it a K list. Suppose if there are K colors, you call it a K list. You attach a K list at each vertex. A K list of colors. Now you have to pull out one color from this list and give it to that particular vertex. You color the vertex by the chosen color. Well, your aim is to get ultimately a proper coloring for the graph. And what is the minimum size of the list that you require? That is the listochromatic number of the graph. So you have the chromatic number and the listochromatic number. So at each vertex you have a list and a K list, and you have to pull out a color out of the list and then give it to that vertex. The resulting color must be proper. So at each vertex V of G, a list LV of K colors is given. We have to choose a color out of the LV and give it to B. The resulting coloring must be proper. Now, you say that G is K list colorable. If given an arbitrary K list, that is important. The word arbitrary is important. Whatever be the K list LV at each vertex V of B is given, then it is possible to extract a color from L and give it to B so that the resulting coloring is the proper coloring. Now, the K lists may be identical or they may not be identical. They can be the same list throughout. That is also possible. Okay, next one, please. Now, you say that G is K choosable if G is K list colorable. The two concepts are one and the same. You say either it is K choosable or K list colorable. So what is K list colorable? At each vertex you have a K list and then you have to pull out a color and then color the vertices. Resulting coloring must be proper. So what is the choice number or the list chromatic number of a graph G? It is denoted by chi LG, L for list. What is that? It is the least K such as G is K list colorable. It is the least K so that G is K list colorable. Next one. Now, one thing is obvious, that if G is K list colorable, then G is K vertex colorable. The reason is that, suppose G is K list colorable, you give the same list 1, 2, 3 K at each vertex. 1, 2, 3 K, 1, 2, 3, 1, 2, 3 K, 1, 2, 3 K at every vertex. Then it is possible to pull out a color out of each list and give a color, proper coloring. But that is what you may be saying that K is K vertex colorable. So the G is K list colorable, then G is automatically K vertex colorable. And what is the least K for G is K vertex colorable? It is the chromatic number chi of G. And what is the least K for it is K, G is K list colorable? It is the choice number chi L of G. And I already mentioned to you that the chromatic number is always less than or equal to the choice number. The chromatic number is less than or equal to the choice number for any graph G. Well, the concept of list chromatic number was introduced by Wiesing in 1976, Russian graph theorists, and independently by Erdős, Rubin, and Taylor in 1980, 4 years hence. Erdős, of course, as you know, is one of the most famous Hungarian mathematicians. Then you have what the Erdős number. That depending upon the number of papers that you have in common with Erdős or his contacts, co-authors, that Erdős number is defined. And he had been a very outstanding graph theorist and probabilist. Been to almost all the countries of the world, going on lecturing, throwing out open problems, and so on and so forth. So the concept of the list chromatic number was independently conceived by Erdős, Rubin, and Taylor in the year 1980. Next one, please. Now, let K be any positive. Now, before that, now how about the difference? So you say that the chromatic number is always less than or equal to the list chromatic number. How about the difference? The list for a graph G, the difference between the list chromatic number and the chromatic number. Well, Erdős, Rubin, and Taylor show that the difference could be arbitrarily large. The difference could be arbitrarily large between these two parameters. So what is the construction? That is a very nice construction. You take K to be any positive integer and you choose M to be 2K minus 1, choose K. 2K minus 1, choose K. Let G be the bipartite graph KMM. That means there is a bipartition XY. X has M vertices and capital Y also has M vertices. and it is a complete bipartite graph. That means every vertex of x is adjacent to every vertex of y. That is Rubin and Taylor. They show that for the bipartite graph, the chromatic number is just 2. So whatever be k, the chromatic number is 2. So the Erdős E of t showed that G is not k choosable, which means when you take k to be very large, the difference between the chromatic number and the choice number and the chromatic number will get large. That is to say, if you say that it is not k choosable, it means that the chromatic number is greater than or equal to k plus 1. Next one, please. Well, you go to the previous one. Previous one, please. Previous. No, the previous one. Okay. Now, why do you say that? How do you say that the difference between the chromatic number, this chromatic number, and the chromatic number for the graph that KMM is larger than k? Well, there are m you call the bipartition as xy. In x there are m vertices, in y there are m vertices. Now you take m is number 2k minus 1 choose k. So you take each k subset out of this collection and attach one subset to the one vertex. So first subset to the first vertex, second subset to the second vertex, and the mth subset to the mth vertex. This way you have similarly say to do the same thing for capital Y also in the bipartite graph. So you have attached now k subsets at each of these vertices. Okay. Suppose it is I'm saying it is not k choosable. That graph is not k choosable. That means it is not possible to give a proper coloring for this graph KMM. Well, suppose you what about the number of colors that you have given to x? Suppose the number of colors that you have given to x, capital X, k is less than k. So you are given less than k colors to x. Totally there are 2k minus 1 colors. Therefore, the difference is larger than, greater than or equal to k. You have a number that is less than k and you have 2k minus 1, so the difference is greater than or equal to k. That means you are taking, there is another k subset out of this. Now, out of this k subset, you have to choose one color, but that color will not be found in this list because it is in the complement. So this is not possible, which means at least k colors you have to give to x. Similarly, for the same reason, you have to use at least k colors for coloring the vertices of y. And remember, it's a complete bipartite graph. So whatever color you give to x, you cannot give to y, but to any vertex of y. You give any color to x, that color cannot be repeated in the set y, because it's a complete bipartite graph. Any vertex of x is adjacent to any vertex of y, any vertex of y. Therefore, if you are given at least k colors for x, then in the balance, you have to give at least k colors for y, because totally there are 2k vertices. So you are given at least k colors for x and at least k colors for y, but total number of colors this way is k plus k, that is 2k. So at least 2k colors you are using, whereas the number of colors which is sorted is only 2k minus 1. So this contradiction proves that this graph is not possible to color it with the k colors. The choice number of this graph is at least k. So whatever be k, you can construct a graph, namely the bipartite graph KKK with choice number greater than or equal to k. Therefore, greater than k, sorry, is not k, greater than k. Therefore, the difference between the chromatic number and the choice number can be arbitrarily large. Now, look at this one definition. You say that a graph G is degenerate if its vertex set can be linearly ordered as V1 less than V2 less than V3 less than Vj less than Vn. You linearly ordered the vertices so that Vj has at most d neighbors on the left. So you order the vertices linearly like this, so that if you take any Vj, on the left it has at most d neighbors. Okay, for example, I take the graph K35, the complete bipartite graph K35. I say it is 3 degenerate. Why? Well, I take the vertices V1, V2, V3, one part, and then V4, V5, V6, V7, V8, another part. Now start from V1. V1, of course, is not adjacent to any vertex on the left. V2 is not adjacent to V1 because it is in the first part. V3 is not adjacent to V2 or V1 again. But what about V4? Because it's a complete bipartite graph, V4 is adjacent to all the 3 vertices on the left. Similarly, V5 is adjacent to the same 3 vertices. V6 is adjacent to the same 3 vertices. So also for V7 and V8. That means you can order the vertices as V1, V2, V8 so that for any vertex, the number of adjacent vertices on the left is 3 or less. Therefore, it is 3 degenerate. The bipartite graph K35 is 3 degenerate. Well, if G is D degenerate, then G is D plus 1 choosable. If D is degenerate, then that means D is D plus 1 choosable. Why? Because imagine that you have D plus 1 colors at each vertex. You have D plus 1 colors, a bag of D plus 1 colors at each set of D plus 1 colors at each vertex. Well, you suppose you are in a particular vertex, then you on the left, you start coloring from left to right. You start coloring the vertices from left to right. Suppose you are in some particular vertex, say V5. Then look at V1, V2, V3, V4. There are at the most D colors, I mean at the most D vertices on the left that are adjacent to V5. But you have got how many colors here? One more color. You have D plus 1 colors. There are at most D neighbors on the left, but then you have got D plus 1 colors in your bag. So you can pull out one extra color and color it that vertex V5. This you can do it for every vertex. Whatever be the vertex that you choose, on the left you have at most D colors, at most D neighbors. So for these D neighbors, you need only D colors. But then you have got D plus 1 colors at every vertex. Therefore, that vertex can be chosen. You can pull out the remaining color and give it to that vertex. So as you go from left to right, you can color all the vertices using the D plus 1 colors. Therefore, the choice number of this graph is at the most D plus 1. If we have a bag of D plus 1 colors at each vertex, then it will be possible to color all the vertices starting from left to right. Okay, next one, please. Now I look at this particular graph. What is the graph? The complete bipartite graph. One part has k vertices, other part has k to the power k vertices. It's a very nice result. One part has k vertices, another part has k to the power k vertices. And what is the least chromatic number? It is exactly equal to k plus 1. As per the previous theorem, you know it is less than or equal to k plus 1, but you really need k plus 1 vertices, I'm sorry, k plus 1 colors to give a proper coloring to this graph. Okay, by the previous result, you know that the least chromatic number is less than or equal to k plus 1. I now produce a list L for LV for each vertex V, so that it is impossible to extract a proper coloring. I now produce a K list. That means if I produce it, it means it's not K list colorable. But you know, you can always color it with the k+1 colors, which means the list chromatic number is exactly equal to k+1. It is not less than k+1, but it is less than or equal to k+1, therefore it is equal to k+1. So we now produce a k list L for each vertex V, so that it is impossible to extract a proper coloring. Okay. So what is the bipartite graph I am considering? This bipartite graph. Remember, the bipartite graph is k. One part has k vertices, the other part has k to the power k vertices. So first part I call it is A, and the vertices are V1, V2, Vk. The second part is B, and the vertices are U1, etc., Uk to the power k. And the middle one you call it some Ui, which you may take it as U, I1, I2, Ik. This Ui, you call it as U, I1, I2, Ik. Because totally there are k to the power k vertices. So each ij takes k values. Accordingly, you know, you can list them one starting from 1, 1, 1, 1, finally k, 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 etc. So you will get k to the power k listings. Next one, please. Next one, please. Yeah. So here is the list for, so what is the list that I am giving for V1? Well, 1, 1, 1, 2, 1, 3, 1, I1, 1, k. Then for the second vertex, this is LV1, list for V1. That is in the top row of the bipartite graph, top layer of the bipartite graph. For V2, I take it as 2, 1, 2, 2, 2L2, and 2K. For the last one, LVK, I take it as K1, K2, etc., KK. And in between, you have some K, L, K. Okay. So this is for the top layer, V1, V2, V2. What about the bottom layer? I take L for the ith vertex Ui. I take this one, 1I1, 2I2, KIK. 1I1, 2I2, KIK. I take this list. Then, now, you know, I have to color this out of this. This is the bag that is given to the vertex LV1. Suppose I want to pull out some color and color it. Suppose I pull out one I say 1I1. The second one I pull out, say 2I2. The last one I pull out the KI. Then here at the bottom, you have this, you know, the list 1I1, 2I2, KIK for the vertex UI. Yeah, that's how we have defined it. That's for suppose we choose the color 1I1 for V1, 2I2 for V2, etc., then it is impossible to give any color for this particular vertex in the bottom. That means you the chromatic number is actually equal to k to the power k. Next one, please. Okay. Now, what about the list chromatic? I take the complete bipartite graph K and M. What about the list chromatic number? Can you give a bound? That is the question. Well, we can certainly give a bound. That bound is log n to the power base 2 floor plus 2. Now, Reddish and Rubin and Taylor, Reddish, Rubin and Taylor proved this using probabilistic methods. That is to say, the list chromatic number of the complete bipartite graph K and M is upper bounded by the floor of log n to the power base 2 plus 2. But you know, there is a very different proof, a nice proof, without using probabilistic methods. So remember, we are considering the graph K and M. It's a bipartite graph. So let AB be the bipartition of K and M. Let AB be the bipartition of K and M. I set K equal to log n to the base 2 floor plus 2. The integral part of log n with respect to base 2 plus 2. I take it to be K. Now, I consider any k-list assignment. This number is a positive integer. I consider any k-list assignment Vk in M. That the total set of colors used. So I consider what? Any k-list assignment for this graph Vk in M, the complete bipartite graph K in M. I look at the vertex set and then I give a k-list assignment. So first vertex will have some k colors, second vertex will have some k colors, and so on till the last vertex. Now you pull all these colors together, then the total set will be, there may be repetitions, you know. I may give the same color to this vertex and this vertex in the bag. Two bags may contain the same color, that is possible. So pull out all the colors and then the total set be, let us say 1, 2, 3, 4. So totally you are using Q colors. Totally you are using Q colors. And at each vertex you are using, you are pulling out, the list of K list assignment. Therefore, at each vertex there is a set of K colors. Okay. Now the 0th step, start with. I give a weight 1 to each vertex. I give a weight 1 to each vertex. Remember, we are considering the graph K and M. That is, remember, here is read the first line. I was showing that the list chromatic number of K and M is at the most log n with respect to base 2 plus 2. So total number of vertices is 2n. I am attaching weight 1 to each of these vertices. So total weight is 2n. This is the weight, not color. The weight, total weight is 2n. Now what I do is, I look at the vertices in X. I look at the vertices in X. And also the vertices in Y. At each vertex there is a bag of K colors. At each vertex there is a set of K colors or bag of K colors, out of which you have to pull out and color. So when I look at the vertices, so first I look at all these lists and find out which one have color 1. Okay. Suppose for instance, the bipartition, let us call it as, I mentioned that AB, let AB be the bipartition. So in the top portion A, suppose there are 10 vertices that have color 1. And in the bottom, let us say there are 6 vertices with color 1 in the list. Because 10 is greater than or equal to 6. What I do is, I pull out the color 1 out of these 10 bags and color the 10 vertices of A. The top layer, I pull out the color 1 from the bag that contains the color 1 and then I give the colors to those vertices. Okay. Now what did I do in the start with? Start with I gave the color 111, weight 111 to all the vertices of K and N. So what is the total weight? N plus M, 2M. So totally to start with, the weight was 2M. So remember that. Now what is that I am doing? And I'm just giving an example. There are 10 vertices in the top layer in A and 8 vertices in the bottom B, whose the color list contain 1. So I pull out because 10 is greater than or equal to 8, I pull out that 1 in the 10 bag and color those 10 vertices in A. I color those 10 vertices in A. And I double the weight of the 8 vertices in the bottom. I double the weight of the 8 vertices in the bottom. Now, the 10 vertices have no further, what is their job now? They have no role to play. They go to sleep. So what was the total weight contribution by these 10 plus 8 vertices? It is 10 plus 8 is 18. But now the 10 is gone, but 8 has been doubled. So 8 times 2 is 16. But 16 is less than or equal to 18. In other words, by what I am doing, I am not increasing the total weight. Remember, the total weight is 2m. So only thing is, for 10 vertices, I have pulled out the color and colored those vertices by 1. And then for the 8 vertices of B, I have doubled the weight and the color has now, weight has become 16. So 20 greater than or equal to 16. So I color the 10 vertices there and then retain the weight, the new weight 2222 for 8 vertices of B. Okay, that is step 1. What about step 2? What is the next step? I again look at the remaining vertices of X and the vertices of Y. I do the same thing. Find out, I now, because I have finished the color 1, I look at color 2. How many vertices are there in the A part having color 2? How many vertices have weight 2 in B part? So which one is the larger number? The larger number, I color them with the color 2. The smaller number, I double. Suppose they are equal, you can do anything. You can either, double it in A or double it in B. It makes no difference. The ultimate aim is the total weight is not increased. What is the total weight? 1 plus 1 plus 1, n times 1 plus 1 plus 1, n times 2n. So n plus n is 2n. So original starting weight was 2n. At every stage of our algorithm, the weight to total weight 2n is not increased by this process. Okay. Then I look at the vertices with the color 3 and so on and so forth. Now what is it I have done? So when I pull all the color bags, the total number of colors I got was 1, 2, 3, Q. So that was how I just defined the number Q. Total weight was Q. Okay, next one please. So at the end of step Q, I claim that all the vertices are being colored. At the end of weight step Q, all the vertices have been colored. If not, what happens? Well, there will exist a vertex V with the weight 2k greater than 2m. And because how many steps were there? There are k steps. At every step, you are doubling it. 2, 4, 6, 8 like that. So the k steps, there are total weight is 2k. At the end, this particular vertex that has been left out has weight 2k. But what is our k? K is the floor of log 2. I'm sorry, log n with respect to base 2 plus 2. That's how we define the number k. Floor of log n with respect to base 2 plus 2. And you multiply it by 2. It's not at the end of the step, all the vertices are being colored. If not, there is a vertex V with weight. It is 2 to the power k, not 2k. Sorry, because every time you are multiplying by 2, so 2 k times 2 to the power k. But k is log n with respect to base 2 plus 2, so 2 to the power k is larger than 2n. But remember, by our algorithm, we said at no stage is the total weight exceeded 2n. But then now it is exceeding 2n. So your assumption that this number is larger than that number is wrong. Therefore, the choice number is less than or equal to log n with respect to base 2 plus 2. So for the complete bipartite graph k and n, the total weight is log n, as a buffer bounded by log n with respect to base 2, 4 of that plus 2. Next one, please. That is the result of Taylor, Erdős-Taylor, and now these are all some well-known results. So remember what is it? K degenerate. Remember I defined it. K degenerate. Every planar graph is phi degenerate. Every planar graph is phi degenerate. And then if G is the planar graph, if G is the, what is the planar graph? We can embed it in the plane so that no two edges, crisscross. If at all they meet only at the vertex. A graph is planar if it can be embedded in the plane so that the any two edges meet only at a vertex and they don't crisscross. So if D is planar, then the listochromatic number of the graph is less than or equal to 6 because it is phi degenerate. Every planar graph is phi degenerate. So that implies that D is a planar graph means its listochromatic number is at most 6. Now, when you say it is at most 6, the natural question is it possible to reduce it? And when you reduce it, how far can you go down? These are all questions that are naturally asked. So how about reducing from 6? And there is a very celebrated theorem of Carsten-Thomason, which says that every planar graph is phi choosable. That means the listochromatic number is less than or equal to phi. The listochromatic number for every planar graph is at most phi. The reference is given and also given in many textbooks. You can have a look at it. Now, next question is it possible to reduce phi to 4? Is it possible that, so that is a natural question. When you say, originally you said 6, because k plus 1 is 6. And then you said by Thomason's theorem, you can reduce it to 5. Every planar graph is phi choosable. So naturally, the next question is every planar graph is 4 choosable. But the celebrated theorem is every planar graph is 4 colorable. But is it possible to say that every planar graph is 4 choosable? Well, if you can say that automatically, because the chromatic number is bounded by the choice number, you can conclude that every planar graph is 4 colorable. Appel-Haken proof is not needed at all. And you don't have to wait, waited for so many years to get the result. But there are planar graphs which are not phi choosable. Is it possible to reduce phi choosability to 4 choosability for planar graph? Answer is no. Yes, please. Here is a very nice example. And so I give you a planar graph which is not 4 choosable. I give you a planar graph which is not 4 choosable. So planar graph means what? You can embed it in the plane so that if two edges meet, they meet only at the vertex. And it's not 4 choosable means I have to give a set of 4 colors, attach a set of 4 colors at each vertex. And then so that it is impossible to extract a proper coloring out of these sets. That is what you mean by saying that the graph is not 4 choosable. Now, this example was given by Choi and Horn on common list coloring, on common list colorings. The Electronic Journal of Combinatorics appeared in 2017. Okay, now I look at, just have a look at this graph. This is a planar graph, as you see. The edges are not crossing each other. If at all they meet only at a vertex. Now, except for these 2 vertices, I give you 4 lists. So, for this vertex, what do I give? 1. For this vertex, I give 2. Right? And then on the left, I give, there is a triangle. And then I give the colors such 1, 2, 3, 4, 1, 3, 4, 5, and 2, 3, 4, 5. And on the right, I give the colors 1, 3, 4, 5. So this is also 1, 3, 4, 5. This is also 1, 3, 4, 5. Here the bottom 2, 3, 4, 5, 2, 3, 4, 5. And in the right extreme, I give 1, 2, 3, 4. And I give 1 here at the top and 2 here at the bottom. And at the middle vertex, I give 1, 2, 4, 5. Okay. Now, remember, because I have given color 1 here, the neighbors of this vertex U cannot have color 1. So, though I have given a 4 list here, this 1 is really useless because I cannot give 1. Similarly, we have at the bottom we have V getting color 2. I cannot give color 2 here. Similarly, on the right, I cannot give color 1 here and color 1 for X3, and I cannot give color 2 for this vertex in the middle and also in the vertex X6. So I cannot give color 2 for X6, and then I cannot give color 2 for the central vertex. I cannot give color 1 for the central vertex, and I cannot give color 1 for this extreme left extreme vertex. Okay. Next one, please. So what is that we have now? So suppose we choose 5 for X4. I take the color 5 for X4. Then we get the triangle. See, X1, X2, X3. I choose 5 for X4. Then we get the triangle X1, X2, X3. Would you please go to the previous one? Previous one, please. Yeah. So here you see, if I give 5, then I what about this? I cannot give 5 here. Though 5 is there, 5 I cannot give. Here also I cannot give 5. I cannot give 1 here because U has color 1. Therefore, this vertex cannot have color 1 on the left. So you get the figure, the triangle that you get in the next slide. Next slide, please. So what you have the triangle X1, X2, X3, and the reduced set of colors you have 3, 4, 3, 4, 3, 4. And you know, to color a triangle, you need at least 3 colors in a proper coloring. With 2 colors, you cannot do it. Therefore, it is not possible to give a proper coloring to this particular graph. Okay. But then the top and bottom vertices have just 1 colors. So what I do is, next one please, the previous one and the previous one. Yeah. So what I do is, I take this one here, this particular graph, I take a K4, complete graph on 4 vertices. For example, ABCD, let it be ABCD. I look at the side AB. Now, I make this vertex U coincide with the A and the bottom vertex coincide with the B. And then I embed this figure above AB. Next what I do is I just reverse it. I make V coincide with the A and U coincide with the B, and I embed this same graph down below. So that the resulting graph is planar. Well, this I do it for each of the 6 sides of the complete graph K4. So I take the complete graph K4, and on each of the 6 sides, I embed this particular graph. Then you find that you have now, because you know that the vertex 1, which is just receiving 1 color, and then you have on the complete graph, you have 4 vertices and 6 edges, and I give 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 in any order you please. Suppose I take one particular edge, 1, 2, then I embed this on this. Similarly, I embed it on others. But whatever the resulting one, next one please, next one, and the next one. So embed H on each side AB of K4 as well as BA of K4, so that the vertices U, V become AB and BA. Now, to these 4 vertices, I attach the list 1, 2, 3, 4, 1, 2, 3, 4 to the 1, 2, 3, 4. There are 4 vertices, and I am attaching 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 and the resulting graph is planar, but it is not fourth-usable. Why is not fourth-usable? We have already seen that. So because 1, 2, 3, 4, if you take the complete graph 1, 2, 3, 4, and you are attaching the sets weight to 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 on the at the 4 vertices. Naturally, all the 4 colors will be represented at the 4 corners. Some vertex must get 1, some vertex get 2, some vertex must get 3, some vertex get 4. Suppose 2 vertices A and B get 1 and 2. But then on the AB, you have embedded that particular graph. And we have shown already that it is not possible to color it if you do that. Therefore, the resulting graph, so whatever way you embed it, is not fourth-usable. So that was the example given that was given. Okay, I think, okay, next one, please. Yeah, the above non-choosable planar graph has 88 vertices. You can easily count it. But then the smallest non-fourth-usable planar graph was due to contains 63 vertices. It was due to Mitsakani. So Bulletin of the Institute of Combinatorics and Applications, 1996, page 15 to 18. Therefore, you have a non-fourth-usable planar graph. So we cannot improve upon the theorem, the Carsten's theorem, that every planar graph is five-usable. We cannot improve upon that because there are non-fourth-usable planar graphs. Next one, please. I think maybe I'll have to okay. So many of these results are available in the book that we just published in 2021. Next slide. It is by myself and Professor Juding Zhu. Juding Zhu is the director of the Center for Discrete Mathematics at Zhejiang University in China. So we have published this book, which is called the Combinatorial Null Zelensatz. So that different topic altogether, but then many of these things come under that purview. And what all I have stated here are also available there in the book. And next one. Next one, please. Yeah. Juding Zhu and Balakrishnan. The title is Combinatorial Null Zelensatz. With applications to graph coloring, CRC Test, Taylor and Francis, published in 2021. The combinatorial null Zelensatz, maybe I will just mention in passing the very famous theorem of Alon-Tarski. I don't know, many of you might have heard about him. Alon-Tarski is the very distinguished professor of mathematics and computer science who holds twin position, one at Tel Aviv in Israel and the other is in Princeton University in USA. So he introduced the combinatorial null Zelensatz. There is a Hilbert null Zelensatz. Perhaps some of you might have come across if you have done some algebra, higher algebra and also algebraic geometry. You will find Hilbert's null Zelensatz. So in analogy to that, he called it combinatorial null Zelensatz. Actually, his proof the main theorem on combinatorial null Zelensatz, we proved that using Hilbert's null Zelensatz. But then much simplified proof was being given later that appeared in the American Mathematical, which just uses mathematical induction. No need to go for Hilbert's null Zelensatz. Null Zelensatz is a German word. Germans have a fancy for pulling together several words together. So here null means the zeros of a polynomial, one polynomial or many polynomial. Satz means theorem. Stellen means location. So you are concerned with the location of the zeros of polynomials. So that is the meaning of the statement and the combinatorial aspects of that. Okay, next one, please. Okay, because I have not discussed the CNS in detail. I don't think I have the time to do that. So with this, I think I will stop. I, I thank the organizers for giving me this nice chance to speak to you. Thank you.
Thank you, Professor Balakrishnan, for your insightful talk.
Yeah.
And I would like to thank everyone who is present here. And thank you, sir, for accepting our invitation for the talk. Is anyone having any questions? Okay, sir. I don't think so that the attendees are having any questions. Thank you, sir. Thank you.
Thank you. I'm really sorry, there had been some problem with the display.
No problem, sir. No problem. It's perfectly fine. Thank you, sir. Thank you for the talk. Thank you.
If I
Okay,
had
sir.
the picture and then I have moved the cursor, then it would have been much more interesting.
Okay, no problem, sir. It was pleasure to have you. Thanks a lot.
Thanks for all. Thank you.
Thank you, sir.